All right, guys, today we're going to do lesson 4.2 notes, which is called L'Hôpital's Rule. This is a French guy. All right, it looks like it says hospital, but it doesn't. It's L'Hôpital. All right, here's how it works. When you're doing a limit, and you might wonder, why are we doing, we did limits this a while ago, but check this out. If you're doing a limit and you plug it in and you get either 0 over 0 or infinity over infinity, we can use something called L'Hôpital's rule, okay? And it can help me find the limit. So L'Hôpital's rule works like this. If the limit of, like, let's say the top and the bottom both go to 0, or if they're both positive or negative infinity, here's what we do. We take the derivative of the top, we take the derivative of the bottom, and then we just do the limit again. And if that doesn't work, you can keep going and do the limit again, and then you can do the limit again, okay? This is how L'Hôpital's works. It basically says you can take derivatives of the top and the bottom separately and keep taking limits, all right? Okay, so check this out. So right now, when I say, like direct substitution, if I say these are both going to infinity, I get infinity over infinity, okay? And so I'm going to go ahead and use L'Hôpital's rule. This stays the same. So this is going to be the limit as x approaches infinity. The derivative of x is 1, and the derivative of e to the x is e to the x. So we use this a lot of times, especially with e to the x, because you take more derivatives and that one stays the same, while the other one like kind of goes away. All right, well, as x is approaching infinity, this whole thing is approaching infinity, and 1 over infinity goes to 0. So I could figure that out. Now that's different than on number 2, when I try to put infinity in e to the infinity over infinity, so it's a L'Hôpital's rule again. So I go like this. The limit as x approaches infinity, and then the derivative of the top over the derivative of the bottom. Okay, now when I go to evaluate this, e to the infinity is infinity over 1, so that one goes to infinity. So these two have two completely different answers, even though from the beginning they both looked like infinity over infinity, okay? Okay, this one is 0. Now watch the same idea. If I plug in, actually, you got to be careful. You might think that L'Hôpital's will work. It doesn't always work every single time. Because if I do direct substitution here and I plug in 0 into x, I get 0 over e to the 0. Well, this is 0 over 1, and the answer is 0. This is not L'Hôpital. Because in order to be, it would have to be 0 over 0. Okay, that's the only time it's going to work. Okay, check it out. Okay, if I plug in a 0, I get 3 minus 3 e to the 0 over 0. And e to the 0 is 1. So I get 3 minus 3, I get 0 over 0. So I'm going to do L'Hôpital's rule right here. So by L'Hôpital's rule, I'm going to get the limit as x approaches 0, and I take the derivative of the top. Well, the 3 goes away. The derivative of e to the 3x is e to the 3x times 3. And on the bottom, the derivative is 1. Now I'm going to go ahead and plug this in. And I get negative 3 e to the 0 times 3. We know e to the 0 is 1, and so I get negative 9. So this went from something in indeterminate form, all right, 0 over 0, this is called indeterminate, to actually figuring out an answer for it, okay? All right, take a look at number 5 and number 6. So when we first did limits, we would start by doing direct substitution, and negative 1 squared is 1, so I get 2 minus 2 over negative 1 plus 1, and I would get 0 over 0. Without L'Hôpital's rule, okay? So the way that we used to do this when we got 0 over 0, do you guys remember? We would factor. So I'd have the limit as x approaches negative 1. On the top, if I take out a 2, x squared minus 1, now I can factor that out to get a difference of squares, x plus 1, x minus 1. Okay? And you guys remember we could cross this out, and that was my removable discontinuity. That was my whole. So this is the limit as I get very close to negative 1, and I'm left with 2x minus 1. And when I do direct substitution now, I get 2 times -2, which is -4. Okay, so we used to do it with this method. We would factor, right? Well, now when I go over here and I plug this in, I get, 0 over 0. But now I'm going to do this with L'Hopital's rule. And hopefully you get the same thing, okay? If I take the derivative of the top, that's 4x, and that goes away. If I take the derivative of the bottom, that's 1. And so now when I do direct substitution, it equals -4. And I got like the same answer. All right, so it just gives us one more way to do limits by taking derivatives of the top and the bottom. Okay, this is saying don't use L'Hopital's rule just because it looks like it should work. Example 3 is not L'Hopital's because direct substitution is not 0 over 0 or infinity over infinity. It was 0 over 1. Okay? So don't use it just like all the time. You have to check first. If using it leaves you with the form 0 over 0 or infinity over infinity, you can use it again. It's a process which can be repeated as many times as necessary. Just remember to use direct substitution at each step to make sure that the rule can be used. Okay, so it's like this. Check it out, you guys. If I plug in negative infinity squared, I get infinity. If I plug in e to the negative times negative is positive, e to the infinity is infinity. So I'm going to do L'Hopital. And I'm going to get, okay, the derivative of the top is 2x. The derivative of the bottom is e to the negative x times the negative. All right? And I'm going to do direct substitution again. So I'm going to check. When I plug that in, that goes to negative infinity. And that goes to negative e to the infinity, which is still infinity. So I'm going to do L'Hopital again. And this time I do derivative of the top. Okay, that's 2. Derivative of the bottom. Okay, that's negative e to the negative x times another negative. Well, that just means I can cancel out those negatives, okay? At this point, when I go to plug in that, I get 2 over, and e to the positive infinity goes to infinity, and anything over infinity goes to 0. Okay, so I can get that way. All right, let's check this out, you guys. Check it first to see if I can actually do L'Hopital's rule. When I plug in 1 here, I get, the ln of 1 is 0. When I plug in 1 here, I get 1 minus 2 plus 1. So I do get 0 over 0. Okay, so I'm going to do L'Hopital real quick. All right, and I get the limit as x approaches 1. Okay, if I'm going to take the derivative of this is 1 over x minus 1, and that goes away. If I'm going to take the derivative of this is 2x minus 2. And now I'm going to check it, all right? Now when I plug in 1 over 1, I get 1 minus 1, 2 minus 2. I still get 0 over 0. So I'm going to do L'Hopital one more time. Okay, and when I do that, I get, let's see. Okay, the derivative of 1 over x, that's 1x to negative 1. The derivative will be negative 1x to negative 2. That goes away. And on the bottom, the derivative of 2x minus 2 is 2. Okay, so I get negative 1 over 2, so I get negative a half. So I got an answer after all that, but I had to do L'Hopital's twice on number 7 and number 8. Okay? All right, perfect. The next part of this video is just for BC. They do a little bit more. If you're an AB and you'd like to watch it, it's always a great idea. Let me show you guys some of the BC stuff. Okay, so this is for the BC notes. AB, you guys can watch this anyways because it's interesting, but let's look at indeterminate forms, all right, in calculus. There are 7, I believe. Let's see if we can take a look here and see what they are. There's 7 indeterminate forms which we typically consider, okay? We got 0 over 0, infinity over infinity. It works with the negatives, with the infinities too. 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. Now, the only ones that I can use L'Hopital's are those first two. Everything else, they're still indeterminate, but I can't use L'Hopital's. So, for example, something like this. Okay, if I were to plug in infinity, now, 1 over infinity does go to 0. So this would be 1 to the infinity. But if you remember, that was one of our indeterminate forms. Okay. This one would be 0 to the 0. That was one of our indeterminate forms. And this is infinity to the 0, because we do know 1 over x. That's going to go to 0. And then this is, the sign of 0 is 0, and 1 over 0 goes to infinity. Okay, so these are all called indeterminate forms. And we can't really do like L'Hopital or anything with those. Okay, you can't tell. All right, you just can't tell. Okay, let's see if we can find a couple of these limits. So this is, we talked about how 1 over infinity is 0. So this ends up looking kind of like 1 to the infinity, which is indeterminate, right? Well, I'm going to show you actually how we can find this limit using our calculator. Okay, so one thing I did is I went ahead and put this in my y equals. I can kind of look at the graph. All right, it looks like it's like flattening out at some point there. So let's say I'm not really sure, right? If I set up my table on Ask Auto and I go into table, now I'm trying to approach infinity. So I'm going to think of big numbers like 10. It's not that big. But about 100, about 1,000, about 10,000. Okay, does it look like it's approaching something? Cool, all right. It's getting really close to this number right here. Does anybody happen to recognize that number? Go one more step. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So I'm not sure if you guys recognize that number, 2.7182818. Check it out. You know what that number is? E, 2.7182818. So this is a really interesting question. If you go on into other levels of math, you'll like definitely look at this. So this limit is actually E. That's where E comes from, honestly, because it's like the limit as that goes to infinity, it gives me that natural logarithm, okay? It gives me a natural E. All right, so this one, x to the 1 over x. So like right now, it kind of looks like infinity and then 1 over x is to the 0. So let's actually see what this goes to. So again, I'm going to use my calculator. All right. Okay, I'm going to go into here and I'm going to go x to the fraction 1 over x. And I'll just look at my table. I've already got it set up. So it gets closer, 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 closer. It looks like eventually this actually goes to 1. Okay? So I can kind of look on my calculator and see that that limit goes to 1. Interesting, right? Okay, and then this last little part we'll talk about real quick. Sometimes limits can be evaluated quickly using the concept of relative growth rates. Rank the following in order of growth as x approaches infinity from slowest to fastest. Okay, let me graph these real quick. Okay, so I put these all in here. These are the different growth rates of things, right? So x squared grows like that. Okay, 1, obviously that is no growth rate. That's straight across. X to the first is a very slow rate of growth, and then x squared is the second. So I think those are my, well, I know that y equals 1 and y equals x. Those are my lowest growth rates. Is that right? Well, let's look at this actually. ln of x, so as this is getting bigger and bigger, it does tend toward infinity, but it goes very, very, very slow. Even that's moving faster. Okay. X to the 10th, that'll get there a little bit faster than that, and then e to the x. All right, so check it out, you guys. My lowest growth rate is this line right here, y equals 1. So let's get this up here. So ranking these from slowest to fastest. So that's going to be the slowest growth rate. My next one actually looks like it's going to be ln. ln grows barely faster than 1 does. And then my next one is going to be y equals x. My next one was going to be y equals x squared. So the only ones I'm having trouble is which grows faster, x to the 10th or e to the x. Well, let me get rid of the rest of these. And let's see which grows faster. I mean, it looks like, you know, x to the 10th is getting up there pretty quickly. And e to the x is like this, but let's just like spread out a little bit more and see. Eventually what you're going to see, doesn't happen for a while, but e to the x eventually does take over x to the 10th. It actually reaches infinity faster. It does. So this would be 5, and that would be 6, okay? Exponentials, where there's an x in the exponent, those grow faster than anything else, all right? So like knowing that, look, as this is going to infinity, which of these is growing faster? Well, e to the x is growing very fast. So the bottom will be bigger than the top, so it goes to 0. And like here, e to the x grows, oh, as we approach 0, actually, I should probably know what the graphs of these look like. Well, e to the x grows really fast. It looks like that. And when I plug in 0, e to the 0 is 1. ln of 0, you guys, ln looks like that. What's happening as I approach 0 from the right? Negative infinity. And 1 over infinity will give me 0. That is it.